Welcome back to Hands-on FPGA Design, from theory to implementation. I'm Albert. Today, we are diving into Lab 5, building an SoC system with custom AXI slave interface circuits. This is a highly critical lesson, as we are stepping up from merely using off-the-shelf IPs to developing our very own hardware accelerators. Let's do a quick recap of our course progress. In our previous labs, we have already become familiar with building a complete SoC system. Today, we will be implementing an AXI slave interface circuit. This step is not only crucial to fulfilling our current computational demands, but more importantly, it lays a solid foundation for handling master interfaces and managing more complex system integration down the road. Here is the outline for today's session. Before we begin, please ensure that you are fully prepared. For detailed content, please refer to the pre-lab course. There are 3 core objectives for this lab. First, to gain a deep understanding of the AXI bus protocol operations. Second, to learn how to utilize the Vivado IP packager to package our custom slave interface. And finally, to configure the correct address mapping. In terms of logic functionality, we will implement an arithmetic logic unit, ALU, that can display operational values, operational modes, and execution results. Meanwhile, the onboard LEDs will change their states dynamically according to the active operation mode. For example, when mode equals 3, which represents the division operation, 2 specific LEDs on the board will light up. We will input 2 operand values for the computation, and the final results will be output directly onto the terminal. Next, let's get down to AXI Lite. It is a simplified version of the full AXI protocol. In real-world hardware designs, we typically don't use it to transfer massive amounts of data. Instead, it is primarily dedicated to reading and writing control registers. AXI Lite possesses 3 key characteristics. First, its burst length is strictly fixed at 1, meaning each transaction maps to exactly 1 data payload. This dramatically simplifies the underlying control logic design. Second, it has a fixed data width, supporting only 32-bit or 64-bit configurations. This standardized width makes interfacing with the CPU extremely intuitive. Third, it features a highly streamlined architecture. Since it eliminates the need to handle complex burst transmission logic, it consumes very few hardware resources, making it perfect for resource-constrained control paths. After walking through AXI Lite, let's explore a key question. How exactly does the processor communicate with our custom IP? This brings us to the 2 most critical concepts within the AXI protocol: data channels and the handshaking mechanism. As you can see on the slide, the AXI protocol splits data transmission into multiple independent channels. First, AW stands for the write address channel. Its job is to tell the slave which memory address to write the data into. Next, W is the write data channel, which actually transfers the data payload. Then, B represents the write response channel. After the slave successfully receives the data, it sends an acknowledgement signal back to the master, ensuring that the write operation is truly complete. However, having channels alone isn't enough. We need a strict set of rules to guarantee data integrity, and that is what we call the handshake. Every single channel we just introduced features a crucial pair of control signals, valid and ready. We can visualize this as a conversation between 2 people. When the transmitter has data prepared, it asserts the valid signal, essentially saying, "Hey, I have a data entry ready here, I can send it to you." On the other side, if the receiver is not busy and ready to take it, it asserts the ready signal, replying, "No problem, I'm free right now, send it over." At this point, please commit one critical rule to memory. A data transaction is successfully executed only at the clock rising edge where both valid and ready are simultaneously high. This is the absolute essence of the AXI handshake. Lastly, AXI Lite also includes 2 read channels. AR is the read address channel, which tells the slave from which address you want to fetch data, and R is the read data channel, which allows the slave to return that data to the master. Naturally, the exact same handshaking rules apply here as well. Next, let's examine our experimental circuit. To start off, the CPU issues a write command. At this moment, the data payload travels through the AW and W channels we just discussed, and writes directly into the slave interface. Once the slave receives this data, it immediately hands it over to our ALU IP core to perform the computation. After the operation is complete, the CPU will issue a read command, fetching the execution results back from the slave's internal registers via the AR and R channels. Additionally, the CPU can also interface through this exact same slave module to control the onboard LEDs. You can reference the actual block design layout right here in the bottom right corner. Inside our slave module, there are 4 registers in total. The CPU writes the operation mode into register 0, and the 2 operand values into register 1 and register 2. The ALU core we designed will then read the values from these registers, perform the computation, and store the final execution results back into register 3. Next, let's examine the specific memory addresses that correspond to these 4 registers. The CPU will route and write the data based precisely on these address offsets. Here is our lab workflow diagram, which is primarily divided into 3 main sections. First, we have the ALU block. Next is the PL side, and finally, the PS side. You can download the required source code examples for this course from the link provided. Now that we have wrapped up our communication architecture, let's shift our focus to the ALU source code. First, let's look at the module definition and declarations on the left half of the screen. As you can see, both input operands are defined as 8-bit, while the mode selection signal is 2-bit, which aligns perfectly with the 4 operation modes we discussed earlier. Finally, for our operation output, we declare it as a 16-bit wide signal. This is a critical design choice to ensure that when a multiplication is executed, the product won't suffer from any overflow. Next, let's examine the logic implementation on the right side. This block is similarly triggered by the rising edge of the clock. We utilize a case statement to decode the operation mode. Whenever the mode is 0, 1, 2, or 3, the hardware will immediately perform the corresponding addition, subtraction, multiplication, or division. At the very end of our logic, we've implemented a safety mechanism. If the mode falls outside these 4 standard cases, the output defaults to 0. Moving on to the software implementation phase, we will write C code to drive the hardware circuit we just built. At the very beginning of our program, we declare our variables inside the function. Next, we call the out32 function to write our operation mode and operand values directly into the slave's internal registers. Once the hardware completes the computation, we immediately follow up with the in32 function to read the execution results back from the target register. To guarantee data integrity, we've integrated a segment of readback verification into our code, which means we perform an extra in32 operation to fetch and verify the exact data we just wrote. Finally, we utilize printf to display the retrieved values onto our terminal, wrapping up the entire workflow. Let's start our project now. First, open up the Vivado tool and click on Create Project. Name this project Lab5_ALU. Select RTL project and check the box for Do Not Specify Sources. Switch over to the Boards tab. Select the ZedBoard. And click through to enter the main workspace. Next, click Add Sources on the left menu. Choose Add or Create Design Sources, and click Create File. Name the file Lab5_ALU. Once initialized, you will see the newly created file appear under the Design Sources hierarchy. Double-click to open it, and copy and paste our sample ALU Verilog code right inside. Following the same steps, click Add Sources again, but this time select Add or Create Constraints. Click Create File. Name it lab5_ALU. Open the newly generated constraints file. And copy and paste our sample pin assignments template. With both the RTL and constraints files ready, click Run Synthesis on the left menu. Once synthesis completes, simply click Cancel on the pop-up prompt. Next, go to the top menu, click Tools, and select Create and Package New IP. Select Package your current project. When the Package IP tab appears, navigate down to Review and Package, and click the Package IP button to wrap up our custom ALU core. Once packaged, we can close Vivado. Now, relaunch Vivado. Click Create Project. And this time, name the project lab5_example. Choose RTL project, check Do Not Specify Sources. Select the ZedBoard as usual. And enter the workspace. In today's lab, we are going to practice designing a custom AXI slave interface. Go to the top menu, click Tools, select Create and Package New IP. And this time choose Create a new AXI4 peripheral. In the name field, enter lab5_slave. You can review the AXI slave parameter configurations right here. For this lab, we can simply leave everything at their default settings. Next, select the Edit IP option, which will launch a separate temporary project window for editing our slave peripheral. Under the Design Sources hierarchy, open the two automatically generated Verilog source files and copy and paste our customized slave interface code templates right inside. Now that our circuit logic is integrated, switch over to the Package IP tab. Click on Customization Parameters and click Merge Changes from Customization Parameters at the top. Next, navigate to the Review and Package section and click Repackage IP. Vivado will ask whether you want to close this editing environment. Click Yes to return to our main lab5_example project workspace. With our IP blocks fully prepared, it's time to assemble our system. Click Settings on the left menu, navigate to the IP directory, and open the Repository tab. Click the plus sign and add our custom lab5_ALU IP into the project repository. Next, click Create Block Design on the left menu to open up the IP diagram workspace. First, click the plus sign to instantiate our processor core. Type Zinc and select the Zinc 7 processing system. Once it appears, click Run Block Automation at the top banner to let Vivado automatically route the connections for fixed_IO and DDR. Click the refresh icon on the toolbar to clean up and regenerate the layout. You should now see a clean processor core on your screen. Next, let's call out our custom slave interface. Click the plus sign again, search for slave, and select lab5_slave. Once instantiated, click Run Connection Automation at the top banner. Check the All Automation box, click OK. And click the refresh icon one more time. You will notice that Vivado has automatically wired the master-slave interface bus between the CPU and our custom peripheral, and it has also added the processor system reset block to perfectly synchronize all system clock and reset domains. Now, we need to export an external port to drive the onboard LEDs. First, select the ALU_mode signal on our block, right-click, and select Make External. Select the newly generated external port and rename it simply to LED. Next, click the plus sign once more to instantiate our ALU core. Selecting ALU. We now need to manually hook up the ALU ports to their corresponding interface ports on the slave block. Please follow the wiring connections as shown on the screen. Once you complete the wiring, your diagram layout should look exactly like this. Next, switch over to the Address Editor tab at the top panel. You can see that our custom slave peripheral has been automatically mapped to the base address 0x43C0_0000. Whenever the CPU wants to control this slave unit, it will communicate directly through this specific memory space. Once verified, head back to the diagram view and click the checkmark icon on the top toolbar to run Validate Design. Next, go to the Sources window, right-click on Design_1 under the Design Sources hierarchy, and select Create HDL Wrapper. Choose Let Vivado Manage Wrapper and Auto Update. Once finished, the tool will automatically generate a top-level Verilog wrapper that ties together all the underlying IPs inside our block design. For our physical connections, click Add Sources on the left menu. Select Add or Create Constraints. Click Create File. And name it Lab 5. Open the newly created file and copy and paste our sample system pin constraints template. Now, we need to adjust our FPGA fabric clock speed. Go back to the diagram view and double-click the Zinc processor block to open the Recustomize IP window. Switch to Clock Configuration and expand the PL Fabric Clocks directory. Because our custom ALU IP is optimized for a maximum frequency of 50 MHz, we need to change clock 0 to 50 MHz right here. Click OK. Next, hit Run Synthesis on the left panel. And click Cancel on the subsequent pop-up prompt. Please look closely at this step. Because the internal clock constraint within our standalone ALU IP and the processor's fabric clock FPGA_0 are essentially tracking the exact same physical signal, Vivado might treat them as two conflicting domains during different compilation phases. To resolve and consolidate this, right-click on our ALU IP block and select Edit in IP Packager. Under the Constraints directory of this temporary project, locate lab5_ALU, right-click it, and select Remove File from Project to get rid of this duplicate constraint file. Once removed, click File Groups and select Merge Changes. Finally, go to Review and Package and click Repackage IP. Once back in the main lab5_example project, click the IP status banner at the top. Select Upgrade Selected at the bottom panel. And then click Rerun to apply the changes. Now we are ready to kick off the final hardware compilation. Click Generate Bitstream under the left menu and let Vivado execute synthesis and implementation. Once the bitstream is generated, click Open Hardware Manager to check our device state. Next, go to the top left corner, click File, navigate to Export, and select Export Hardware. Make sure you check the box to include bitstream to generate our complete XSA hardware platform wrapper. Once exported, click on Tools from the top menu and select Launch Vitis IDE. Confirm your workspace directory and click Launch to enter the Vitis dashboard. Click on Create Application Project. Switch over to the XSA tab at the top banner and select the XSA platform file we just exported from Lab 5. Name our software project Lab5_test. Expand the SRC folder on the left Explorer tree. Open up helloworld.c and overwrite it by copying and pasting our sample C code template right here. At this point, we need to perform a critical manual override. Because we introduced a heavily customized IP core into our hardware system, we must manually modify the compilation makefiles so that the compiler can properly link our libraries. There are 3 separate makefiles that require updates. Here is the path to the first one. Simply open it and copy and paste our modified makefile template over it. Moving on, here is the second path. Overwrite its makefile in the exact same way. And finally, here is the third path. Paste our updated template here as well. Once you've entered the workspace, please follow the diagram to connect the ZedBoard using cables and turn on the physical power switch. At this moment, the green power LED will light up. With the makefiles updated, let's open our terminal. Go to the top menu, click Window, navigate to Show View, select Terminal, and it will open up at the bottom right. Click Open a new terminal and select Serial Terminal. Choose the correct COM port mapping corresponding to your computer's connection. Set the baud rate to our maximum standard speed of 115,200 and click OK. Now, select our hardware platform directory under the left Explorer pane and click the hammer icon on the top toolbar to build the platform base. Once that completes, select our application system directory down below and click the hammer icon again to compile our C source files. Finally, go to the Assistant window on the bottom left, right-click on our system project application, navigate to Run, and select Launch Hardware to deploy our firmware onto the Zinc CPU core. Upon successful execution, you will see the runtime results print out instantly inside the terminal window at the bottom right. As you can see, our operational mode is configured to 3, which represents the division operation, and our 2 input operands are set to 6 and 3 respectively. The terminal accurately outputs a final result of 2. This perfectly validates that both our underlying ALU hardware logic and our iLite register read and write routines are functioning flawlessly. Furthermore, we can perform a dual verification by observing the physical LED states on our ZedBoard. Notice that the two rightmost LEDs are currently lit up together. This perfectly matches the specific hardware state we defined for mode equals 3. This proves that when the CPU issues computational commands, it also successfully commands our hardware peripherals through our custom iSLAB registers. Now, feel free to modify the input values in operational modes inside helloworld.c yourself, re-execute the program, and observe how the system dynamic outputs change in response. Through today's experiment, we have successfully walked through the entire pipeline of custom RTL circuit design, iLite bus interfacing, and software-driven hardware deployment. In our upcoming labs, we will build upon this foundational architecture to design even more sophisticated IPs and handle advanced data processing workloads. Looking ahead to our next lesson, today we learned how to utilize iLite to read and write control registers to manage an ALU. However, in real-world system development, if we need to process larger blocks of data, relying solely on a handful of registers creates a massive bottleneck. Therefore, in our next class, we are going to introduce an extremely vital hardware resource, VRAM or block RAM. In Lab 6, we will implement an VRAM controller, enabling the CPU to directly map and access memory blocks inside the FPGA fabric. This milestone means the CPU can burst write entire batches of data into VRAM or read back massive blocks of processed results simultaneously. I'm Albert. Thanks for watching, and I'll see you in the next class.